Okay, so last couple weeks we've been talking about probability. We know probability has to do with likelihood or a long time average outcome. Now we're going to talk about probability distributions. So first new definition, a random variable is a variable that represents the possible outcomes of a random process. Possible outcomes. We typically use capital letters from the English alphabet to represent random variables. So you'll see capital X, capital Y, capital Z. Those are really common. Any capital English letter is fine. Choosing a letter that matches the variable you're representing is common. So if you're representing cost, you might use a capital C. Yeah. The probability distribution is then a list of all of the possible outcomes and their corresponding probabilities. And we can represent it two ways, either with a table or a graph. We're going to look at both. We're going to start with a table. And the example for our table, we're going to construct a probability distribution. Distributions, why does that say distributions? Because I'm a doofus, that's why. Shouldn't be there. Try that again. Construct a probability distribution for the random variable x, where x represents the number of heads out of 3 flips of a fair coin. 3 flips of a fair coin. So in order to build a probability distribution, first I have to know what my sample space looks like. I need to identify all of my possible outcomes. And then I need to group them according to that random variable, which is number of heads. If I am flipping 3 coins, or doing 1 coin 3 times, what is the minimum number of heads I could flip? 0. I can flip no heads. I could get all tails. Good. What's the maximum number of heads I could get? 3. All 3 were heads. So I suspect the values are 0, 1, 2, 3. And I'm going to group my sample space by that so I can see what it looks like. So I'm going to start with the no heads. If I have no heads, what does my outcome look like? Tails, tails, tails. 3 tails, yeah. So tails, tails, tails. That's the first category here. Next, I'm going to go with 1 head. That's 3 possible outcomes. I could have gotten the head on the first flip. I could have gotten the head on the second flip. I could have gotten the head on the third flip. Okay, next one is the row for 2. 2 heads, which means that third outcome must have been a tail, yeah? So similar idea, that 1 tail could have been first. That 1 tail could have been second. Or that 1 tail could have been third. And then the one possible outcome that's not up there is 3 heads. Yeah. Do we agree I've got all the possible outcomes? See some nodding. Yes. Good. I made 2 choices times 2 choices times 2 choices. I should have 8 outcomes. And I see 8 outcomes up there. Perfect. So I'm going to write that down because that is important. There are 8 outcomes in my sample space. Which means when I go to calculate my probabilities, the denominators of those fractions are going to be 8. 8 possible outcomes. Let's fill in our table. For the first row, how many of those 8 outcomes have no heads? 1. Probability of 1/8. Yeah. And we'll grab a calculator in a minute. of those 8 outcomes, how many of them have exactly 1 head? 3. Out of those 8 outcomes, how many have 2 heads? 3. And then I have 1 sad guy by himself. That's all 3 heads. Good. And we know we prefer decimals rounded to 3 or 4 places. So 1/8 is 0.125. And 3/8 is 0.375. And that is how we build probability distributions. Look at all the possible outcomes, categorize them by random variable, how many heads, right? Find the probability. Not too bad. Not too bad. It turns out that these random variables that we're keeping track of, in this case number of heads, can be discrete or continuous. Those are words we've heard before. Who remembers what a discrete value is? What does it mean for a number to be discrete? If you can't define it, can you think of an example of something that's discrete? Number of pages in a book. Perfect. Very good. Jeanette, what else? Another example of something that's discrete? Yes, Julia. Very good. Number of students in a class. You'll notice both of those were number of something. These are typically, countable things. These are things that we're counting, yeah? So these are usually things we are counting. 0, 1, 2. I'm never going to get a fraction. I'm not going to get like 1/2 of a person or 1/2 of a book page. What about continuous? Yes, Theo. Very good, and that's true here. These things can be decimals. We looked at height, right? Length, weight, time on a stopwatch, things that we measure. Those same definitions apply to random variables. A discrete random variable is something that is countable. 0, 1, 2, 3. Yeah. Continuous random variables can take on any value on a number line. We're going to start with discrete random variables in this unit, and then in our next unit, we'll start looking at continuous random variables. So for the rest of Unit 4, we're focused on this first box, discrete random variables. And the first thing that we should know about discrete random variables and their distributions is that probability distributions for a discrete random variable follow the same rules that any probability follows that we saw in the first half of Unit 4. So there are 2 things we know about probabilities. Every probability should be a number between what and what? 0 and 1. Perfect. Never happens, always happens. Somewhere between those two extremes included. Yeah. If I take all of the probabilities for all of the possible outcomes in a sample space and I add them together, what should I get? 1, because that's 100% of the sample space. Same thing is true here. And the question is, does that hold for our probability distribution for flipping a coin? And I see some nodding. All of these numbers are between 0 and 1. They're decimals between 0 and 1. If I add up those probabilities, what do I get? 1. I get 8 out of 8, which is 1. Perfect. Perfect. Happy face. Okay. So we're going to do an example together. The example says, U.S. Census Bureau collects data on the number of vehicles owned per household in the U.S. We will ignore the very small percentage of houses that own more than 4 vehicles. Let V equal the number of vehicles owned by a randomly selected household. The probability distribution of V for a recent year is given in the table. What is the, write the event, household owns 1 vehicle in terms of V, then find its probability. What's the probability that a randomly selected household owns at least one vehicle? So first thing I do when I see that kind of table and they've told me it's a probability distribution, I want to check it meets requirements. So the probabilities they've given to us, all between 0 and 1, did they give us all the probabilities? No. Frowny face. And you'll notice that's question A. What is the probability that they own exactly 1 vehicle? So first they want us to write it using probability notation. So I'm looking for the probability that V equals 1. And then they want us to find that. How can I find that? Does anybody have any ideas? Take a minute, talk to your neighbors. How can we find that missing probability? That's not very nice. Or synergistic. All right, who's got a suggestion? We're complaining about our teammates. We've clearly gotten off task. Who's got a suggestion? Yes, Ava. Very good, because we know they should add up to 1. So 1 minus the sum of all of those other numbers. Add up all the numbers, subtract it from 1. If you want to do it in your calculator, you can type it exactly like we wrote it. If you don't use parentheses, the calculator will do it wrong. Parentheses are your friend. When I do it, I get 0.34. Yeah. So I can go back up here. I know this is 0.34. Nice, pretty complete probability table. Now we can answer B. Whoops, that's not how I meant to write that. And B says, what's the probability that a randomly selected household owns at least 1 vehicle? So first question is, how do I write that using probability notation? So P, I know there's a V, I know there's a 1. What math symbol represents at least 1? Greater than or equal to. Very good. At least means greater than or equal to. 1 is included, everything bigger than 1 is included. So this here, in my probability distribution, are these outcomes here. So what can I do to find this probability? Add them all up. So that's one possible solution. So 0.34 plus 0.37 plus 0.14 plus 0.06. Or how else could I do this? Yes. This is 1 minus P, B equals 0. 1 minus the only thing I didn't circle. And that gets me the answer a lot faster because I'm pretty sure that's 0.91. And I can do that subtraction in my head faster than I can do the 4 additions. Yeah. So with discrete random variables, once I know what my discrete random variable is, I know what my sample space looks like, building a probability distribution for it is helpful, because then I can answer questions more quickly about the system. Yeah. We all look wide awake today. Okay, so table is great. There is another thing that we can do to represent a probability distribution, and that is draw a picture or a graph. Specifically, we are going to make a histogram. I know, and we gross, but it's not gross. It's not gross. All you have to remember, random variable goes on the X, probabilities go on the Y. From there, it's not so bad. Because this is discrete, this is going to look like a box, not a box, a bar chart, but the bars touch. I should zoom back out. You guys are going to have to give me numbers for this because I can't get my table and my graph up here. But let's go ahead and draw our graph. So we want the x-axis to be our random variable b, which is number of cars owned, yeah? And in my table, what were the possible values of v? 1 through 4? 0 through 4? 0 to 4. Okay. So 0, 1, 2, 3, 4. And then on the y-axis, I want to plot probability, P of V. In that table, what is the largest probability? 37. So I need my graph to go up to at least 37. 38 or 40 is probably better. So let's see. 10, 20, 30, 40. I think counting by fives is probably the easiest. So 5, 10, 15, 20, 25, 30, 35, 40. And then we make some bars, and our bars are going to be centered about their label. So for No cars owned. What's the probability that a randomly selected household has no cars? 9%? 0.09? So that's going to be just a little bit less than 0.1. And if I wanted to make that really clear, what could I do? Very good. 0.0. Perfect. Next category, what is the probability a randomly selected household owns one vehicle? 3.4. So a little bit less than 3.5. And then I think 2 was 3.7. I have notes here. I can just look. Next one is 1.4. So just under 15. And then 0.6. I see people using color, people using rulers. I like those things. Yeah. Does that process feel vaguely familiar? Yes. Good. Good. Because we are looking at discrete, the values of the variable are going to be in the center of the boxes. Boxes should be equal width. Boxes should touch because we're on a number line there. We're treating them as if they were continuous. Yeah. Not so bad. Questions before we do another example? No. Okay, so next example. It says high school students in Michigan sometimes get snow days in the winter when the roads are so bad that school is canceled for the day. Define the random variable S as the number of snow days at a certain high school in Michigan for a randomly selected school year. The table gives the probability distribution of S, which is at the top of the next page because I ran out of room. So we see a table of snow days. Smallest is 0 for no snow days. Max is 10 for 10 snow days. And it says, number 1, find the probability that snow day equals 0. Describe this probability in words. 2 is if there are more than 6 snow days in a given year, the school year will be extended. Find the probability that this happens. And 3, make a histogram of the probability distribution. Describe its shape. That it gets extended? I mean, they still have the same number of school days. It's 180 days. It's just... Yeah. As somebody who lived where there used to be snow days, I'd still take the snow days in a longer school year. Snow days are nice. Waking up and seeing everything covered in white so you didn't have to get out of bed was a nice feeling. Okay. We'll start with the first one. We want PS equals 0. PS equals 0. Vishal, how do we find that? How do we find that one missing probability? Perfect. Very good. Add them all up. Subtract it from 1. So 1 minus, and then the sum of the others. So 0.19 plus 0.14 plus 0.10 plus 0.07 plus point, where did I stop? 0.05 plus 0.04 plus 0.04. Oh my goodness, this is a long data table. Plus 0.01 plus 0.01. And I got 0.33, and I hear a yes. Yay. Which is the biggest number in the table. So more often than not, no snow days. You okay, Brody? That's okay. Next one says, if there are more than 6 snow days in a given school year will be extended. Find the probability this happens. So in that problem, I want probability V, and then I see a 6. And the question is, I need to know what math symbol goes between the V and the 6. Ooh, I heard a greater than. Why greater than? Good. It said more than. It didn't say at least. It didn't include the 6. Good. So greater than, more than, which means I'm going to start in my table not at 6, but at 7. Those are the probabilities that I have more than 6 snow days. So those are the probabilities I'm going to add. 0.04, 0.02, 0.01, 0.01. 4, 5, 6, 7, 8.08. Did I do that correctly? I see some nodding. Thank you, Caleb. 0.08. Very good. And then the last one says make a histogram, which is why I was leaving some space around the graph here. So we'll start with the easy part. We know, oh my gosh, nobody called me on this. I wrote V. That's not V. What should that be? That should be S. We're looking at S. Snow days. I was thinking last example, snow days. We're plotting S on the x-axis. We're plotting P of S on the y-axis. And I need to figure out how to get 10 on my graph. 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Oh, that's going to be gross. Okay. Yeah. This will not look pretty. But I think that's probably the best way to do that. And then for my y-axis, what is the biggest probability? 3, 3. So I need to figure out what to count by. 3, 6, 9, 12, 15. I don't think is going to fit. But I don't want to count by 5s because that's going to be too big. Maybe 4s. I see some nodding. So 0.4. I guess I could do it right here. So 0.4. Oh my gosh, why can't I write today? So each hash mark, 0.04, 0.08, 0.12, 16, 2, 0, 2, 4, 2, 8, 3, 2, and then 3, 6, which will be a little bit bigger than we need. Yeah? Did I do that right? Okay. I think I know how to count by 4. It's a Monday. It's questionable. And we're going to draw our bars. That's not so bad. So our first bar for no snow days, we decided was 33%, probability of 0.33, which is right up here. And I want to go half my box. Yeah, I know. That's just because I didn't make my grid big enough. But that's where that first one would sit. Centered about 0, yeah? For box 1, what was my probability? 18. 19. 19% chance I have exactly 1 snow day. So 19 is sitting right here. Box is centered about 1 because that was S is 1. Next one, 2 snow days was 14. Next one is 10. Four snow days is 7. Five snow days is 4. 6 snow days is also 4. Yes? No. 5 snow days was 5. Nobody called me on that. 5. And then 6 is 4. 7 is 4. 8 is 2. 9 is 1. 10 is 1. Yeah. Notes doesn't have to be perfect, just got to be on the page. Yeah. While you're sketching, it is. That's okay. While you're sketching, does the shape of that probability distribution look similar or different to the last graph we drew? Different, right? Very different. The peak is in a wildly different place. Those conversations that we had before about the shape of a distribution, we can do that for probability distributions as well. This guy is right skewed, heavily so. Yeah, very strong peak on the left, long tail on the right. I'm going to go back to our last graph. How would we describe the shape of this distribution? Unimodal, very good, nice clear peak. Is that peak kind of in the middle or clearly off to one side? It's kind of in the middle, not perfect. A little bit of a longer tail over here. But vaguely symmetric, definitely unimodal. Yeah, good. So those discussions about shape and the terms that we used before still apply to this type of distribution, just like they did any other type of distribution. Yeah? In addition to sharing those terminologies for the shapes of their graph, we can also use some other quantities that we use to describe quantitative variables. We can discuss measures of center. Where is the center of the probability distribution? And measures of spread. How spread out is it compared to its measure of center? So we're going to start that today and then probably finish it tomorrow, because I don't think we're going to finish it today. We're going to start with measures of center. And we know that the default measure of center is the mean of a distribution. The mean is the default. And when we talk about probability distributions, more often than not, they're not going to call it the mean. They're going to call it the expected value. So when we are talking about probability distributions, expected value just means the mean. And what it is measuring is the long-term average if I were to do this thing many, many times over and over again. Repeated trials of flipping 3 coins, interviewing household after household after household about their cars. Many, many trials, long-term average outcome. So for any given probability distribution, if I want to find the mean of that random variable x, I can write it as the symbol for mean, mu sub x, or I can write it as E of x, the expected value of random variable x. Both of those represent the same thing. And it turns out calculating it's not too bad. To calculate the mean or expected value, I'm going to take each x value and I'm going to multiply it by its probability. I'm going to do that for each column in the table or each row in the table, multiplying down or multiplying across, depending on how it's built. And once I have multiplied every possible outcome by its probability, I am going to add them all up. You can do this by hand, which is what we're going to practice in the next example. Or you can do this with your calculator, which is what we'll show at the beginning of class tomorrow. Okay. So, example says, earlier we defined S to be the number of snow days at a certain high school in Michigan for a randomly selected school year. Calculate and interpret the expected value of S. Calculate and interpret the expected value for S. They use the phrase expected value and not mean, so I'm going to write E of S, because that's what they said. And to calculate the expected value or the mean, I take every possible outcome and I multiply it by its probability and I add them all up. So I am going to go through this table. I'm going to multiply and add, multiply and add, multiply and add. So first possible value, 0 snow days. What was its probability? 0.33. Perfect. And then I am going to add to that 1 snow day. What was the probability of 1 snow day? 0.19. Perfect. Plus 2 snow days was 0.14. Yes. 3 snow days was 0.10. 4 snow days was 0.07. 5 snow days was 0.05. 6 snow days was 0.04. 7 snow days was 0.04. 8 snow days was 0.02. 9 snow days was 0.01. 10 snow days was 0.01. Yes, a lot of writing. As a side note for the FRQ, when you are doing examples like this, where there is a long string of multiplication and addition like this, but it's the same thing over and over as you work through a table, it is okay to write the first 2 terms of the pattern and the last 2 terms of the pattern. So yes, a dot, 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 but don't not follow it up. Come on, pen. On the FRQ, that second line is enough to show the pattern if you don't want to have to write it all out because you're time pressed. I wrote it all out because I want you to see where it's coming from. This is the first time we've done it together. But on the FRQ, it's okay to shorten when it's repetitive. Just show enough that they know you know the pattern. And now we do the typing. I got 2.17. Caleb got 2.17. Now that I have my 2.17, what else do I need to do? Interpret the value. Very good. If it's FRQ, you should never just calculate, you should interpret. 2.17 what? Snow days on average. So over the course of many years at this high school, I expect to see an average of 2.17 snow days per year. When you are interpreting an expected value or mean for a probability distribution, it is important that you indicate it is a long-term average over many years, yeah, over repeated trials. I need to indicate this is an average over a long repetition of the thing. Some of us are really chatty and we don't have the grades to back up our mouths. Frowny face. Yes, Ava.
Why is that row 3 after the 9 one?
Oh, that was the page number. That right here? Yeah, that was the page number that was pre-printed. I happened to go over the space on my page. I'm sorry. I know. Infinite whiteboard is so nice. It's so nice. What time is it? 30. We got 5 minutes. Okay. So one quick concept. We talked about two measures of center. We talked about measures of center before, median and mean. We use the mean when the distribution is symmetric, the median when it's not, or when there's lots of outliers. We can do that here with a probability distribution. You can find the median. The median is the smallest x value for which the cumulative probability equals or exceeds 0.5. Because we know the median sits at exactly the halfway point, the 50% mark. Cumulative means add as we go. So all we need to do is find the cumulative probability, and once we reach or exceed 0.5, that category is our median. So let's do that really quick. We know this question mark was 0.33. So this first one is 0.33. 0.33 plus 0.19, 0.52, plus 0.14 is going to be 0.66. We've already found where we exceeded 0.5. We exceeded 0.5 here. Yeah? So my median is 1 snow day. What was our mean? 2.17. Notice our median is smaller. I expect that because this was heavily skewed. This was right skewed. My mean has been pulled to the right of my median. That's exactly what I expect to see based on the graph for snow days. Yeah. Not scary, hopefully. Just add until you reach 0.5 or exceed 0.5. Good. Okay. When I see you tomorrow, we're going to talk about measures of spread, and I'll show you how to find both of these things on your calculator. And then we will start the next section, which is on transforming probability distributions. If you have questions, I'll be around after school. Please don't forget to turn in your assignments today. You've got till midnight. If you have questions about your unit project, I'll be available after school. And we have a stats club meeting tomorrow at lunch.